Okay, so let's resume. One thing I do have is I've graded all of the midterms. So if you're here today in class, you can pick them up from me. If not, I'll leave them with the TA for you to collect. And I thought I'd mention just briefly the exam scores, which were out of 100. I have 1, 2, 3 in the 80 to 90 range, 2, 3 in the 70 to 80 range, and 2 in the 60 to 70 range. So that's how the distribution of the scores turned out to be. In general, what I observed was that most of you got that first question with the short answers reasonably right, but of course that was also meant to be just a simple summary of things we've covered in class, and you had the course notes in front of you, so I wasn't particularly surprised that everyone did well in that, but I'm glad you did anyway. I also found that most of you, so sort of most got all of question 1 right. Most got, let's say, much of question number 4 right. Now this was the question about graph coloring. One thing they often did not get right, assuming they did the coloring correctly, is the following fact. The coloring produced by GVDO may be optimal, but is not guaranteed to be optimal. So when we write down that relationship that you have a certain lower bound on the chromatic number and an upper bound on the chromatic number, most of you found the lower bound was 6 and the upper bound was 6. You got a coloring from GVDO that was sort of 4 colors. There's no guarantee that the 4 colors found by GVDO is the chromatic number of the graph, that it's the best possible way to color the graph. I think exactly one student wrote that down explicitly. Many of you replaced this chromatic number with the number 4, which is incorrect, because unless you can justify it. I mean, it may actually be the case that for this graph you can't do any better, but then you would need to prove that, and that's generally a non-trivial thing to do. Right? In fact, I can't even think of any obvious way one can prove that in general without trying all the possible things with 2 and 3 and showing that none of those work out or something like that. So unless you have a way of demonstrating that on this graph there's no way to color it with 2 or 3 graphs, 3 colors, the fact that GVDO returns 4, and it may well be optimal, but there's no proof that it is. And so you can't just say this is equal to 4 without some justification. So I was looking for some thinking through of that issue. So this is one thing I wanted to mention. But really, most of you got much of this question right as well, which accounts for really the fact that many of you have scores in the range of, definitely above 60, but sort of 70 and above, which is the 40 plus 30 you could get out of these 2 questions. However, questions 2 and 3, no one got either completely right, although a couple came very close, and those were the students who got the sort of above 80. Most got both wrong. Some got part of one right, something like this. So basically, generally, I was very unhappy with the solutions as I saw for questions 2 and 3. And I was thinking about sort of what to do about it, and certainly we're ready to move on in the course to the rest of the material, which is going to be at higher layer. So everything we did so far in the course was about the file layer and the link layer, and certainly both questions 2 and 3, which have to do with power allocation over multiple channels and interference, in this case for fixed power, but sort of it's related to the power control and our SINR modeling topic. They're really sort of fundamental things we should understand about the link layer before we move on. So that in conjunction with the sort of, scores not being very high, I thought I could offer kind of a makeup opportunity. And so I've asked the TA to post an individual, in other words, not to be done in pairs, not to be done in pairs, not to be discussed. Extra credit assignment. And the extra credit assignment has basically asking you to solve and write up questions 2 and 3 by hand, and also turn in, actually I would say code and turn in programs that solve them numerically. And part of this is that, of course, in an exam we can't, allow you to sit down and program it, but sometimes, and I find definitely in many of the assignments we've been giving you programming assignments, it's helpful just to build that intuition by writing a piece of code that solves it and is this correct, and you can tinker with a lot of things. So really that individual extra credit assignment is asking you to both solve it and write it by hand mathematically, but also write code that implements the solutions to question 2 and 3 and turn in those programs. I've asked the TA to basically specify what the input and output format for each of those 2 questions should be. He's going to modify this, but roughly, so basically see the posted assignment for details. So he should have it posted hopefully by late today, if not tomorrow, for exact details. But roughly, this is what they're going to look like. So for question 2, which is about the base station interference problem, we're specifying the format of the input and the output that your code should accept and put out. Both the input and the output are basically text files. For question 2, the input basically takes in a bunch of parameters. Input file specifies all of these things that we talk about. So in fact, let me even take notes from my. So the input file will specify, for example, and look at the exact details in the assignment. I don't want you to write it based on what I'm writing here, but roughly speaking, it's something like this. Okay. So all of these parameters that are in question 2, the input file would specify as numbers. So there'd be a number for the power of the base station, a number for the radius of each cell. D0 is our parameter for the reference distance. K is the path loss of the reference distance. T will be the threshold you use. N will be the noise power. Sigma square will be the noise variance in the dB scale. P will be that probability for the second part of question 2, where you have to ensure that the probability of SNR falling below the threshold is below this probability P. And so the output file specifies basically 2 distances. Let me just call it dA and dB, where this is the distance with no fading to ensure the SINR is bigger than T, and this is the distance with fading to ensure SINR, the probability that SINR falls below T is below some probability P. Right? So there's just 2 numbers that should be output. So if you know everything about the system, how far away should I space my base stations if there is no fading, if there is fading? Okay. Which is what the question asked you to solve. But now you're just doing this as a program. So you write this piece of program that must accept an input file in that format and must spit out an output file that has just 2 numbers in each row. So each number in a different line is what I asked him to describe. The code itself that you write, I've asked that it be in either Matlab or Python or C. If for whatever reason you have a different programming environment you write all your code in, you need to check with the TA to make sure he can verify your solution when you provide it. Basically, he just has to be able to run the program. He will have the input files, run your program, look at the output files your program generates, and need to make sure that that answer is correct. For this extra credit assignment, there is no partial credit. So if you write a piece of code that almost works, but there was something in your code that was a little missing, and it would have generated the right answer if somebody had just figured that out and changed it, you're not going to get credit for that. Okay, so this is an extra credit. You have to get it right. The whole score for this extra credit will add a +10 to your midterm score. Okay. Again, it's an individual. Think of this as like a take-home exam, basically. It's like a follow-up exam. You get to add 10 more points to your midterm. You write the solutions up, both the written solutions as well as the code, and you get one more chance, basically, at these 2 questions. Question 3, the same type of idea is that you're going to write a piece of code. It's going to take an input file, and it's going to throw an output file. The input file in this case, so in this problem, there was actually a part B to it, which asked you to kind of figure out the power allocation when you have an arbitrary PMF. So this is the problem when there's 2 channels with arbitrary PMF for, I think the way I specified to him in the email was G over N, but it should be N1 over G1. Okay, N2 over G2. I'll email the TA to make sure that that's clear. So you're going to specify, specifying the PMF for any one channel will take up 2 lines, and specifying it for the second channel will take up 2 lines. Why is that? Because if I think of the PMF, so basically any PMF describes the values. So if you have some random variable x, you have to describe what values it can take on and corresponding probabilities, right? So for example, this is just a toy example that I think might show up in your written description. So it might look something like this. So plus 1 line for total power. Okay, so this is the input file. So what does that mean? It means that for channel 1, the possible values that your channel condition can take on are 1, 3, or 7. And it takes on 1 with probability 0.2, 3 with probability 0.6, 7 with probability 0.2. Channel 2 can take on values, so these are for channel 1, these 2 are for channel 2. The possible values it can take on are 0.5, 4, 10, 20. These are the probabilities with which you'll take on those values, and 10 is the total amount of power you have available to split between the 2 channels. The output of the program is just a single, it's 2 numbers, which are basically the power that you're going to put on channel 1 and the power you'll put on channel 2. Right? And they should add up to the total power that you have here, as you can imagine. Okay, so what those programs should do should be pretty straightforward to understand. And again, you're responsible for making sure that the code is correct, not almost correct. Okay. And quite frankly, that's to save the additional overhead of having to debug your code for you. If you're in an environment, you're asked to deliver a product that does something, you should just do that. It shouldn't almost do that. Okay. I think that's not an unreasonable request to make. So at the end of it, whatever you turn in, both the written part of it as well as the code, will be graded, and we will add, depending on how much of what your total score is, that it'll add up to that fraction of an additional 10 points to your midterm score. So if you had, I don't know, for example, 75 on your midterm, you could potentially raise it to an 85 by doing this assignment. Okay, but most importantly, do it on your own and do it exactly right. So that's what I wanted to say about the midterm. And really, I'm hoping that by having a little bit more time to think about it, you have all the time in the world to get it right. That'll still be a meaningful experience for you to take away from what we've done in the class so far on those topics. So let's move on. And we said that the way the course has been organized is roughly looking at things in the reverse order of the protocol stack. We started by looking at some issues at the physical layer. Then we've been talking about the link layer and medium access issues. Now we're basically ready to talk about the network layer. And in some sense, by moving beyond the link layer to the network layer, for many wireless networks, the network layer is not even really a wireless network. So if you look at your traditional types of devices, everything from Bluetooth to Wi-Fi to your cell phones, really the wireless part of that wireless network is only up to the link layer. Once you get your data to the access point, from that point on, the rest of the layers of the stack are typically a wired network, okay, in most cases. However, there are increasingly new kinds of multi-hop wireless networks that are emerging, and so I thought we'd talk about those a little bit to motivate the kinds of ideas we'll be discussing now. But it's also important to keep in mind that a lot of these ideas are either just starting to be implemented or are in the process of being emerging in products and technologies around us. And although they've been topics of research since the 90s, it's really, I think, the last few years that people have developed real products that use some of these ideas that we're describing now. Okay, and they haven't quite hit mainstream in many ways. So, so really what we want to think about are examples of multi-hop wireless networks. So I want to basically touch on a few examples of multi-hop wireless networks. So first of all, let's clarify what we mean by a multi-hop wireless network, and the simplest way to do that is to contrast it with, for example, your typical Wi-Fi deployment where you have an access point, you have a set of mobile users, they talk to the access point, and then from this point on, it's sort of generically part of the internet cloud, right? So any data that you're communicating in either direction, only this hop of it is wireless. Everything else may be, in most cases, it's just a wired traditional internet. So now, multi-hop wireless network, in some sense, we're implying that your wireless devices are doing something like you're sending data wirelessly to from node A to node B. The data then gets forwarded from node B to node C in a further step, and maybe node C might further move that data to another node, and somehow all of these are wireless links, right? So that's our notion of a multi-hop wireless network. So at a very high level, if you have to think about what these multi-hop wireless networks might look like, a key dimension for classifying them is the amount of mobility. The amount of mobility and the sort of a related point of it, and the kind of density of the network. So at the simplest example of a multi-hop wireless network, we talk about sort of static networks. And as the name suggests, what we mean by static networks is that those nodes in the network are not even moving. So it's very different from your cell phone system in which each user that's carrying the mobile device can be going anywhere. So in a static wireless network that's a multi-hop network, all of those nodes will somehow be fixed at a particular location and not mobile. And there's sort of two or three different classes of multi-hop wireless networks which kind of have this feature. One is a class of networks that is sometimes called a wireless sensor network. And more broadly these days, these types of networks are being referred to as IoT, low-power networks. And another class of static networks that ends up sort of being encountered is a network that sometimes referred to as a mesh network, but really a static mesh network for just sort of providing wireless access. So I'll go a little bit more in detail and describe examples of these, but let's kind of continue at that high level first as we vary that dimension of mobility. So the second level of this multi-hub networks in terms of having mobility is a class of networks that we sometimes refer to as mobile ad hoc networks. And with mobile ad hoc networks, the idea is that they are multi-hop. The nodes are mobile. And in some sense, always or most of the time, the network graph, if you will, is connected. Okay. And again, I'll talk a little bit more and give some examples, but this is a key aspect of a mobile ad hoc network, is that not only are the nodes moving around, but they're not moving around in such a sparse environment or so far away from each other that you cannot get a message from one node to another node right away. I mean, or through multiple hops, but right away. And really, it's meant to be contrasted with the third type of multi-hop wireless network that has many names, but I think a good unifying name for them is an intermittently connected mobile network, in which nodes are mobile and may not be always or even often in range of other nodes. So somehow think of the mobile ad hoc networks as really being more densely deployed, whereas the intermittently connected mobile networks are more sparsely deployed. And sparse in the sense that the sheer number of them in the area of deployment is relatively low. So by way of motivating these different types of networks, I thought I could actually just show you some real-world systems that do things like this. So maybe we can use the browser here. So if we can switch to the big screen, please, the computer screen, please. Yeah. So as an example of these wireless sensor networks, I wanted to, I know it's got acquired now, but I think it'll show up if I did this. So here is a company called Linear Technology that sells a product for wireless sensor networks and has developed this over many years. And you can kind of see from even just this picture It's sort of showing a bunch of these little wireless gadgets. They may have sensors associated with them. They may be deployed for certain industrial applications. They can be deployed, for example, on city streets for doing smart parking and so on. And the idea is that these little wireless devices, they're typically running on low-power embedded processors, and each one of them is taking some measurement. They're doing some local processing if needed, but they're communicating it to wherever the final access point that needs to collect the information is through multiple intermediate hops. And so dust networks, I forget if they have any numbers here, but a colleague that I'm aware of who works for them or works with them said that they have a very large, thousands of customer networks they've already deployed. In fact, I just see the number here. So they claim to have deployed over 50,000 such multi-hop wireless networks in the world in over 120 countries. So that's an incredibly large scale of deployment, actually, for a technology that really only dates back to the early 2000s. So about 2004 or so is probably when they started getting to the point where they could really implement something real. They, in this page, which I recommend browsing if you're interested, also pointed certain standards that are out there. Wireless HART is an example of a standard that is relevant to these types of networks. So if you go to wireless HART, this is a standard for industrial sensing and control using static wireless devices. So a lot of companies where they may have a chemical plant or some kind of a process, and they have different parts in that process where they want to measure what's happening to the chemicals or change some parameters in real time. Traditionally, they used to use wired networks in order to do the sensing and control. The problem is that the wiring costs are quite significant, and also they're very hard to change once you are trying to evolve your plant, whereas wireless deployments are somewhat easier to deploy and modify and seamlessly vary over time. And so this is a particular standard that is in use in a lot of those types of applications. So that's certainly something you might be interested in following up and learning about. If they have some other examples here, it might be good. So let's see. Streetline is a particular company that is using the modes from linear technologies and deploying parking solutions. As I mentioned to you, here's an image. I don't know how easy it is for us to see, but it's basically like a little device that can be embedded into the road. And inside this is a wireless sensor that can measure if there's a car parked on top of it. And this can communicate with other devices on the parking meters as well as other devices nearby. So if we kind of look at Streetline networks, here's their company. Let me see if there's any good visualizations of their system, but basically they're providing everything from street level sensors to mobile apps, parking analytics for cities to deploy these technologies. And it's one of the ways in which cities can immediately find out locations where cars are overstaying, and they can direct their ticket collectors to basically, or ticket issuers to go and do that very quickly. It also provides for customers to have apps that can tell them where the parking availability is at a given time and so on. But all of this is being powered at the core of it by a mesh network of multi-hop wireless devices. So that's actually, from that perspective, a good example. I don't know if they have any good visualizations of their mesh network. I've seen one in the past, but I'm not. Yeah, it's just an infographic. Actually, let me see if there's any images of Streetline networks. So here's sort of a visualization of what they're doing. It's sort of, whether it's lamps or parking meters have some of these nodes. The parking spots themselves have some of these nodes, and they're all communicating with each other wirelessly. So that's sort of one concrete example of a wireless sensor network of the type that we're describing. I mentioned mesh networks. There's a company out in Boston called NetBlazer that uses multi-hop mesh networks to provide broadband access to users in downtown Boston. And again, I wish there was a good image that shows their network. They used to have these in the past. Let me dig around their site a little bit. So here's a little bit of a visualization of what they're doing. So there is a central point in the city where they might be getting their high-speed access from. Wherever that point is, they will have wireless links going between buildings from the place where they have the high-speed access to relay points that will collect that data coming in and can disseminate in either direction to other buildings. And the core idea of the mesh network that they deployed was that all of the, so it's based on just standard 802.11 technology, but their routers that connect buildings have directional antennas. And that's one way for them to increase the signal strength and reduce the amount of interference from other devices within that network. And so it's sort of a directional multi-hop mesh network that's at the core of their system. And if you're kind of interested in how they're able to leverage this into providing high-speed access, certainly you can look at some of their maps here. And again, maybe a search for an image might be a little bit more illustrative.
Is it faster to just pull wire?
It's not a question of faster, it's a question of cheaper. So these high-speed connections that they have are available in certain buildings and not others. And this is sort of their example of why their business model is worth pursuing, is that the buildings that have that extremely high-speed access to it, today if you go look and see how much they're charging for high-speed access, they may be very, very reasonable. In other buildings which are far away from those high-speed access points, the bandwidth is much more expensive, so sort of 2 orders of magnitude difference. So their point is that if you can create mesh routers that can beam that data back and forth between these buildings efficiently, that could bring down the cost. So, and they have a very interesting model also in that each building or business owner that will deploy their system, essentially they're paying for their own piece of equipment, but ultimately then you create this cooperative broadband network where you share you get some of the resources, but you're also helping to build the network out and continue to act as a relay for other nodes in the network. So it's sort of this example of what's called a cooperative broadband network. But the key point is that each one of these things is a wireless node that's communicating with other nodes wirelessly. There's multiple hops that the data traverses both to and fro. Okay, and this is a real-world deployment that's in practice running a business that seems to be doing pretty well. Okay, here's actually a visualization of maybe their actual deployment. Let me see. So this, actually, I know George. He was, I think his son or daughter went to USC, so I met him when he came to USC, which is how I got to learn about some of the details of their deployments. And so this might be like the source, a building in which they have the high-speed access, and each of these links represent other buildings to which they were connected. So these two examples are of static multi-hop wireless networks of the two categories I mentioned, wireless sensor networks and mesh networks. The other category that's of interest are actually, before I go there, let me just mention one more class of things. So these are not commercial deployments, but there is a lot of interest in it. Is a routing protocol called RPL, for example. Here's a CFP for RPL. And it's basically a routing protocol that's meant for these types of low power and lossy, really wireless networks. And this is more of an IETF standard. I mentioned wireless HART, which is more of an industry standard. IETF has its own working group focused on something sometimes referred to as 6-LoWPAN or IPv6 over low power wireless networks or personal area networks. And so there are standards out there like RPL as well, which target this domain. More recently, there is a protocol for low power networks called Thread. Let's see if that comes up. So Thread is a group that's an industry alliance. This is about 2 years old, which includes Nest, the company that builds the smart IoT systems for home, including HVAC applications and so on, as well as a bunch of other companies. And they came up with a multi-hop routing protocol for use in these low-power devices called Thread. And unfortunately, they haven't made the stack open just yet. I think it became open recently. But it's another example of a multi-hop wireless protocol that industry is developing or pushing for use in applications for. In this case, a lot of the applications have to do with maybe home automation or home IoT systems. So these are sort of a few examples of multi-hop wireless networks that are static. Then when we talk about multi-hop networks that are mobile, where all of the nodes might be moving around, a particular example of such a network that's been commercially developed and made available is from a company called Trellisware. So mobile ad hoc networks are sometimes called MANET or MANET, depending on how you want to pronounce this. And this particular company based in San Diego happens to be also co-founded by faculty who are at USC. Professor Keith Chugg, for example, is one of the co-founders. And there was another faculty member as well. And they are developing these mobile ad hoc network devices for tactical applications. So you want to imagine things like firefighters, for example, where individuals are carrying around these radios, and the environment in which they're deploying has no infrastructure. So it's not that you're in an environment where there's already cellular access or Wi-Fi access. You're in some environment where there's absolutely no wireless network established. And the reason they're called ad hoc networks is that they're sort of being created on the fly for the requirement of that particular mission, tactical mission, and not sort of an infrastructure that you're deploying for long-term operation. And so the idea is that there's a bunch of people just carrying around these radios. Any two of them may not be in direct range of each other, so the data might have to multi-hop through intermediate radios. But it allows this whole team of individuals, and they can still be fairly far away. The numbers specified here, for example, is 26 miles per hop. So the individuals can even be separated by as much as tens of miles. And the network itself can have as many as 8 hops, 200 plus nodes. And in such an environment, it's able to make sure that they can talk to each other end to end, basically. And so that's one commercially available tactical mobile ad hoc network system. They've used it, for example, for the Boston Marathon on board Navy ships and so on. And there's sort of real deployments of these. And by its very nature, because it's assuming that there is no infrastructure in place, it tends to be used in more sort of non-traditional type of environments. It's not for your commercial radio access necessarily. The third type or third class of mobile ad hoc networks, mobile multi-hop wireless networks is what I refer to as intermittently connected mobile networks. And by way of examples, let me see if I can find, there's one technology out of Australia called the Serval project, where the idea is to create this type of mobile network. Actually, Serval can also be seen as more of the mobile ad hoc network in its simplest form, because it allows two mobile phones to talk to each other even outside of the standard cellular environment. But in principle, it also has this mode where if nodes are not directly in contact with each other, they will store their data and carry them around, and when they are in range of another device, then they will hand them over. Other examples of where you might see these types of networks emerging is in the context of what is sometimes called DSRC, V2V systems, and maybe I don't have a single point to show us, but maybe I can kind of look at these. Examples anyway. So here's a random image taken from looks like a government website. The idea is that in the future, the government is going to require car manufacturers to put radios in their cars that can talk to other cars on the road, on the order of tens of meters from each other. And in the simplest setting, it might be that all of these nodes that are talking to each other are all within range of each other, like in the mobile ad hoc network. But with this capability of cars being able to talk to each other, particularly if you imagine either more rural areas, remote highways, or even in urban environments, but in residential areas in the evening, you may not have enough connectivity that there's always a bunch of cars that can talk to each other directly. It may be that they're communicating data to each other, and then as they move through the environment, they're able to deliver this data to other devices when they happen to encounter them. To give you another kind of example of this, I could show you a concept video from my lab. Maybe we just need to see if we can find that one. So here's a proof of concept of using intermittently connected mobile network modes on these vehicular fleets. So the idea here, and what we're going to see, is a simulation based on real traces of vehicles, taxis in Beijing. And the two schemes being shown to the left and right are two particular ways of disseminating data between these taxis. So whenever the taxis get close enough to each other, they can transfer whatever the file is that they want to transfer to each other. And in the left-hand side is sort of the easier scheme to understand. It's just whenever they meet another taxi, they hand over however much content they can during the encounter. And so initially, a set of taxis had the content and they were read. And over time, as taxis encounter each other, they get portions of the content, which makes them blue color. And eventually, when they get the whole file, they become red. And they can continue to spread this information throughout the network. And so there's sort of an epidemic process by which the data could be disseminated between the nodes. But the communication only happens when vehicles are close to each other. And so, examples of applications you might envision for this way of communicating between wireless nodes on the road might be, for example, firmware updates. If you look at your cars these days, they're ranging anywhere from being semi-autonomous to eventually maybe completely autonomous. They're going to be increasingly software-driven platforms. If you look at Tesla cars, for example, they sold the actual hardware of the car before it became semi-autonomous. So you actually had to get and download a piece of software that would make it into a semi-autonomous vehicle. And so that download, over time, they might need to update it. They might have to issue security patches. And so instead of having you turn on a Wi-Fi access point or cellular in order to do that, if it's not super time critical, could it be something that they might be able to disseminate? As you encounter other Teslas on the road, you get portions of the code that you need. Eventually, when you get the full update, it's ready to install, and then you install it. So at least people in industry are thinking about that as one of the ways in which we might offload a lot of the heavy data download from cellular to vehicles. So that's another example of this intermittently connected mobile network. So my point in illustrating all of these examples is that you may not be hearing about these types of multi-hop wireless networks in your daily life or encountering them, but they're definitely emerging. And all of the examples I showed are from the last, I would say, 10 years or so. And it's going to almost certainly be a bigger part of our lives as we go on to what's called the Internet of Things, right? When we talk about smart cities, smart homes, smart buildings, a lot of the smarts that we're getting at is coming from connecting various sensors, various actuators, various devices to each other. And particularly when these devices have to be battery operated, and they're not plugged into the wall somewhere, even the communication has to be wireless. And so we're expecting to see more of these types of devices emerge in our environment. So if I can get back to the overhead screen, please. So if you kind of look at these different types of multi-hop wireless networks that are emerging, what we're really getting at now from the perspective of the class is what are the layer 3 algorithms and protocols we need to support these new class of systems, and how might these layers be different from the way in which we had to design routing for a traditional wired network. Okay. So if we want to start thinking about wireless networks, in what sense they might be different from wired networks, we actually have to go back to the link layer just a little bit to understand the quality of links from a network perspective. What does it look like when you have a router in such an environment? What are the other routers it might be interacting with? What do those link qualities look like? Because it turns out that that's one of the big ways in which wireless networks are different from wired networks is, first of all, in a wired network, you know exactly who your neighbors are. They're the ones with whom you have a wired connection. In a wireless network, it turns out this becomes a little bit fuzzy because, on the one hand, the wireless broadcast medium is a broadcast medium. You can hear potentially anyone that's within range. On the other hand, there are effects like multipath fading, channel conditions, mobility, which means that the topology might be changing pretty dramatically over time. Right? So you can imagine that sort of understanding that topology, understanding what links look like, might be different in the case of wireless networks than in the wired networks, and that might drive some of our design decisions. So one thing that we often want to do at the higher layers when we think about a wireless network is, if you remember early on in the course, we looked at something like bit error rate versus SNR. Okay, and then I think in for example, I forget now, but I think in one of the homework assignments, we might have even looked at things like, if you combine it with sort of SNR versus distance, because that's our radio propagation model, you can kind of compose these two and learn something about the bit error rate versus distance. And in some sense, at the higher layers, this is the type of metric that would interest us, except typically at layer 3, you don't care about bits in error, you care about packets in error, or packets being received. And so typically what we look at is a metric, so if you will, sort of link metric of interest at higher layers, is really sometimes called the packet reception rate, or PRR. Sometimes it's also referred to as the packet delivery rate, but it gets a little confusing because is it for a single link, is it for a multi-hop system or so? We're going to use packet reception rate in our discussion. So packet reception rate is very simple. It's really just the percent of packets transmitted on the link that are received successfully. And in particular, given a modulation scheme slash coding scheme and packet size, there's a one-to-one mapping from the bit error rate to the packet reception rate. Of course, the bit error rate is like something that you want to be as low as possible. The packet reception rate is something you want to be as high as possible. So that's just a 1 minus packet error rate type of thing. But more importantly, this is going from what's the probability you lose a bit to what's the probability you lose the packet, right? A packet is a collection of bits. Naively seen, you could argue that if I lose a certain number of bits in my packet, I lose my packet. The details are a little bit more than that, because losing some of the bits in the packet hurt you more than others. So it may be that your packet has a bunch of dummy bits or padded bits. Losing those bits doesn't hurt you, but losing, for example, the destination address might hurt you a lot because you won't see the packet at all, right, at the higher layers. Or if you have that the packet has some built-in error control coding mechanism, it may be robust to a certain number of errors in the data bits, and so you can maybe handle up to 3 or 4 bits of data being lost, and you can still recover from that without a problem. Right? So it really depends on what your packetization looks like, how many bits there are in the packet, how they're protected. But based on all of that, for any given radio, for any given configuration of that radio, there's a one-to-one mapping between the bit error rate and the packet reception rate. Okay. And so really this type of thinking, you can also then figure out what the packet reception rate would be for a given SNR, and you could plot the packet reception rate as a function of distance. Now, packet reception rate as a function of SNR, typically, there really is a threshold. And if you were to plot this for most radios, and if you allow that, typically when we plot bit error rate, we plot it in a log scale. We look at this waterfall curve. And we also have that the y-axis is like, 10 to the power minus 1, minus 2, minus 3, and so on. Packet reception rate, we're almost talking about like what fraction of these packets got through, telling me that 1/100th of the packets didn't get through, or sorry, 10 to the minus 4 of the packets don't get through is probably a level of detail I don't care about when we talk about packets. We really are interested in values between 0% and 100%. Typically, even 0.1% might be too much granularity to care about. So really, if you tell me that one link has 80% packet reception rate, another link has 80.0004%, I don't think I would care between those two. But if you tell me one link has an 80% packet reception rate, another one has a 88% packet reception rate, maybe that's enough of a difference to make me care, right? So it's really sort of that granularity, and the scale at which we care about packet reception rate is somehow different. And so typically when we plot this, we don't plot it in a log scale, we just plot it from 0 to 100, and in step sizes of 1 or so. So 1%, 2%, 3%, up to 100%. So when you plot it in that scale, so the lowest value here is 0, the highest value is 100%, or 1 if you're doing this in a fractional scale. There's going to be a range of SNR values where it goes pretty sharply from 0% to 100%. Depending on the radio, of course, what that this might still be in your dB scale, but there's going to be some SNR threshold above which you're almost 100% likely to be getting all your packets. So when we talk about the outage probability, for example, in our earlier part of the course, we're really kind of talking about this threshold such that after it we have a pretty high guarantee that the packets are going to be received reliably, maybe 95% probability that I get the packet. Okay, and so when I have that threshold decided, I have a very high chance that all of my packets are getting through, regardless of well, in this case, this is with for a given, so long as the SNR is above this value, I have that my packets are coming through. SNR versus distance, we've looked at, if you think of noise as just a constant, the signal itself is decaying with distance. There is some relationship that you can establish, as we saw, depending on the simple path loss exponent, add to that some fading models such as log normal fading, and what you really have is some distribution that the SNR takes at different distances. Okay? If you put this figure with this figure, you can derive what the packet reception rate as a function of distance looks like. And so imagine what you have to do. So for every distance, you look at the range of SNR values, and that gives you a range of different PRR values. Okay? So the question is, are those range of SNR values really sort of below this threshold? Are they above this threshold? Or are they somewhere in between? Because if it turns out that I'm at some what's a good way to see this? So at certain distances, if I'm sufficiently close to the transmitter, even with all the statistical variations, the SNR is above some value. Okay? So let's say that this was my threshold theta. This is our threshold that we're focused on. So in this range, and let's call this the upper threshold. So in this range, even with So if I'm at a distance less than this, even with all of those variations, my SNR never drops below the threshold and I get close to 100% link quality. So up to this distance, let's call that D1, we will have close to 100% packet reception rate. And this is basically saying that if I have my wireless devices close enough to each other, when the transmitter sends, I can get 100% of the packets. If I go too far, and by too far we mean maybe you're looking at this theta lower, there may be some distance beyond which, with all of these statistical variations, I never even go above my lower threshold for the SNR. Okay, so it's like so far away that even with all the fluctuations, it never gets high enough to cross even the lower threshold. So in this case, most of the time, the SNR is basically in this region. Like with all the time, it's with all the variations, it's pretty much in this region. The packet reception rate is close to 0%, and that's like some distance. You know, we're calling it D2 here. After which you're virtually getting no packet receptions at all. But in between these two distances, you're in ranges of distance where the SNR threshold, the SNR values might be spiking above and below, and sometimes they may be above the upper threshold, sometimes they may be below the lower threshold, sometimes they may be somewhere in between. And all of this variation due to multipath fading gets reflected in a big variation in your packet reception rate. So in fact, what you end up finding is that in this range, there's sort of all kinds of different packet reception rates you might encounter. In particular, if you have a slow fading environment, you might be stuck in a bad fading environment here, even though you're at a relatively close distance, and you just get stuck at this value. And if you're farther and farther away, that becomes more and more likely. So there may be some mean packet reception rate curve that's following this behavior, but in slow fading environments, you might be at some point, you know, sort of distributed around that curve. Okay. And researchers who were looking at this problem, including our group here at USC, gave sort of names to these different regions. This is referred to as the connected region. This is the disconnected region. And in between, there's like a transitional region. So what are we saying again? Let me summarize. Okay. If we focus on PRR, this metric of percentage of packets received, for distance less than D1, PRR is close to 100%, and this is what we're calling the connected region. Okay. For D bigger than D2, the PRR is close to 0%, and this is called the disconnected region. But for D values between D1 and D2, PRR shows typically high variance due to fading. Okay. So basically what this fading is doing is sometimes pushes the SNR above the threshold, sometimes below. And if the environment has slow fading, the PRR in this range can be very high or low and stay that way. Okay. In fast fading environments, it may fluctuate over time. And even sort of intermediate fading environments, it may fluctuate over time. And that fluctuation has a big cost when you try to create a routing protocol on top of this set of nodes. If you look at typical radios and what these values might come out to be, so in typical radios, so example, radios that follow the standard called 802.15.4 based radios. They are used in wireless HART, the standard we just talked about. That Linear Technologies company that we browse the website of, they use the networks that they're deploying are all based on 802.15.4 radios. D2 over D1 is approximately 2 to 3. Okay. What does that mean? So imagine here's a node, and I draw a circle of radius D1. I draw another circle that's, in this example, sort of a factor of 2. Or in this example, I guess it's sort of 3. So this is D2. So all of the nodes that are within this distance of this wireless device are going to be in the connected region. They'll get 100% link quality. All of the nodes that are outside this region will get very poor quality. All of the nodes in this intermediate region, they are in that transitional region, and basically it's full of unreliable neighbors. And unreliable in the following sense. Sometimes you'll be able to hear from them, sometimes you won't. So for example, you might have put them in your routing table as a neighbor, and at that moment you put them in, the link quality was very good, and so you're sending packets to them. A little while later, because of the fading effects, the quality has become really bad. Now you're sending packets to them, they're in your routing table, but they're not getting them, right? And so the network performance can really suffer in this case. So if I say the D2 in this example was a factor of 3 from D1, then if I look at sort of a random deployment of nodes, right? So if nodes are deployed uniformly at random, the number of nodes in an area is proportional to the area, right? In a region, let's say. In a region is proportional to its area. So what's the area of the inner circle? It'll be something that's like pi d1 squared. Right? So this is how many very reliable connected neighbors you would have. Okay? Let's call that N1. N2 is the number of nodes that are unreliable, and the area of this region is basically the outer disk minus the inner disk. So this is like, so this is what they're proportional to. This would be proportional to pi of d2 square minus d1 square. And if I assume the d2 is, let's say, as in this example, maybe a factor of 3 of what d1 is, then this would be something like 3d1 square minus d1 square. So it's like 9 minus 1, 8 times d1 square. So if d2 equals 3 times d1, n2 equals 8 times n1. Now if you think about this being a reasonable number, and this is the outcome of that equation, that's telling us that for every one neighbor that I can see that's really reliable, I have 8 neighbors, potential neighbors, that are unreliable. So when I'm trying to create a multi-hop wireless network out of this, a lot of the nodes that I'm hearing from, I'm only hearing some of the time. 80% of the nodes I'm hearing from, 8 out of 9, which is even more than that, right? 88% of the nodes that I'm hearing from are unreliable. Okay. So that's a pretty big deal. And when people first started to deploy these wireless networks, they ran into this problem, that they were taking ideas from wired networks, trying to deploy them in wireless networks, and very quickly originally they thought if you could hear from a node, let's call it a neighbor, let's then do multi-hop routing. But if you did that, so many of your neighbors would be so flaky that you'd be sending packets to them all the time that don't get through, and the whole system is very unstable and very low efficiency. It was very typical in the early days of multi-hop wireless networks to hear reports of a network that barely delivered 20% of the data that was trying to be sent over it. Okay. And so over the past 10 years or so, we figured out how to solve these problems and bring it to the point where we get over 99% reliability in the networking. In fact, if you remember in the linear networks example, if you go to that website, it has actually a statistic specifically on their front page that talks about 99.999% data reliability. And the way they're able to achieve that essentially is to limit communications to nodes in the connected region. And how do you ensure that is an immediate question that arises when you design a wireless network. So to have a high reliability network, you basically have two choices, right? So choice one is filter out all neighbors not in the connected region. And this filter out goes by the name of blacklisting, and this whole general approach is called blacklisting. So it says you identify, maybe you can observe over a period of time. You may not know the actual distances of your neighbors, by the way, because it's a wireless network where it might be deployed indoors, it might be deployed in a factory. There may be no measurements of actual locations that are part of the network protocol. So the only way you can infer whether nodes are reliable or not is to observe them over a period of time. So blacklisting basically says observe your neighbors, identify based on your observations which nodes should be considered reliable partners, and you keep them in, and anyone else you blacklist them. You put them in a list and you never treat them as a neighbor to send data to or from. Okay. So that's a basic idea called blacklisting. I haven't actually seen how the dust networks or the linear technologies networks are deployed to ensure that high reliability they're talking about. My gut feeling is it's because of blacklisting. So they've sort of identified or deployed the networks in such a way that they ensure that every node has a sufficient number of neighbors that are of high quality. And everybody else you do not communicate with. Okay. Related to blacklisting is kind of a deterministic topology construction at deployment time. So what I might do is that I might say that the network I want to deploy, has to have these 3 parking meters and these 6 parking spots all connected to an access point over here. I can make sure that these distances are such that, in fact, if I put these nodes down, that the link quality is sufficiently high. If for any reason it's not, I might deploy additional nodes when I'm deploying to make sure that each node has at least 1 or 2 highly reliable neighbors to send their data through, and place additional nodes as needed. So basically at deployment time, I'm constructing a topology that guarantees that the network that I'm deploying, all of these links in that topology are links that are close to 100% reliable, that are within that connected region. And the topology is almost kind of hardwired at deployment time. Any other link, say, between this node and this node might be possible in theory, but you don't allow it. You just tell this node you're not allowed to talk to that node directly. Your measurement suggests it would be an unreliable neighbor. Okay. So this is sort of one approach to doing it. It has a benefit. The benefit is you get a deterministic high quality topology. You're deploying it, you know what you get. Okay. So sort of the pro is that it's sort of reliable by construction. What might be a negative of this approach? When might it not be applicable? It requires a lot of nodes, right? So it sort of requires high density. So it may be that I only need to connect 3 nodes in my given deployment. They're kind of far apart. And by insisting that all of them be close to 100%, I might require to add another 20 nodes, right? Maybe my application itself doesn't need quite that 100% reliability. It just needs some mechanism that makes the best use of my available node resources, or I want to add a very small number of nodes, not enough to make it so dense that all of the links can be perfect, but allows me some flexibility. Also, if I have an environment in which some of these nodes might come and go, I may not be able to always guarantee that if I require a blacklisting-based approach that I get a connected topology. I might end up with partitions, right? So if I blacklist every neighbor that drops to 90%, my threshold is 95%. If I kick them out of my network, I may be left with a network that's no longer able to deliver data end to end. So an alternative approach to this very strict deterministic blacklisting approach is referred to as basically metric-based routing, where the idea is that you preferentially route through higher quality links. So to give you the context for this problem, consider these 4 nodes, and maybe I have kind of right, all of these links are available to me. I want to route my data from A to B. Now, in traditional wired networks, often the metric of interest for routing is to minimize hop count. So if I do minimize, if I want to find the path that minimizes hop count, I might choose the route A to D, D to B. On the other hand, by trying to minimize my hop count, I'm taking this link from A to D that by definition, because it's reaching farther out, is likely to be a weaker link. And maybe for some reason this D node is in that unreliable region, is suffering fades and so on. And so minimizing hop count results in utilizing with higher probability links that are flaky, links that are unreliable, links that might even be bad. And so this metric of hop count is not a good idea typically in wireless networks. So instead, is there some other metric, let me just call it metric X, that could give me a different route. Maybe can give me the route A to C, C to D, D to B that turns out to be better. And maybe I can't improve on the link from D to B any further because I don't have a choice. But where I had a choice, I was able to improve the quality of that of the path that I get. So what should this metric be? Is the question that arises. We can use an existing off-the-shelf shortest path routing protocol. We can take RIP or OLSR or different existing routing protocols. If we can just figure out what is the right metric to give to them when they decide how to pick a path. Okay. And in this regard, the big development in multi-hop wireless networking was the development, sort of the construction, invention, discovery, development of a routing metric called ETX, which stands for expected number of transmissions per successful reception. So the idea of this metric is very simple. I have 2 wireless devices and I send a packet. If the channel quality is bad for that packet transmission, it might fail. Then I might have to retransmit this packet and it might fail again. I retransmit this packet, it gets successfully acknowledged. So in this particular case, the number of transmissions it took me was 3. I try again, maybe it took a different number of transmissions. I try again, it takes a different number of transmissions and so on. And so the idea is that the expected number of transmissions, so the actual number of transmissions might be a random variable, but its expected value is something that would tell me how good the link is, right? So this is a number that ranges between 1 to infinity, right? It could be unboundedly large if I have a link that's basically disconnected. Any number of transmissions will not get it through. So this is a metric for a link quality such that the smaller this number, the better. Okay. So if we can measure that ETX metric for every link, so there would be an ETX in this case for A to C, there would be an ETX for C to D, there would be an ETX between A to B, there would be another ETX between A to D and so on. So for every edge that I could have in my network, I would have this metric figured out. And the idea is that could I do shortest cost routing using this metric? And how would that perform? Okay. And so what empirically has been found is that ETX turns out to be useful and efficient metric. I guess by efficient, I'm really saying that the network you end up creating using this metric is very efficient, tends not to lose a lot of packets or incur a lot of energy. One reason for this is that ETX captures multiple objectives. So first of all, it favors high PRR links. So if you pick a path where the total ETX is small, you're trying to basically pick individual links that are have ETX as low as possible. If a link has a very high packet reception rate, most of the packets you send go through. The higher that PRR, the lower the ETX. In fact, if you assume IID packet losses over time, then ETX equals 1 over the packet reception rate in the forward direction times the packet reception rate for the ACK packets. So this is forward data packets. This is sort of the reverse ACK packet. So if I have a node A that's talking to node B, it's potentially sending a bunch of packets in the forward direction, and then in the reverse direction you get an ACK. One of the things that can happen is that your ACK might also fail, and if you don't hear an ACK from A's point of view, it doesn't know whether it got through or not. It's going to have to send the packet again, and until it gets a successful ACK, it's going to keep doing it. So if I want to count how many times in expectation I transmit before I get something back, the only event that is success is both the forward data packet needs to be successful and the reverse ACK has to be successful. The probability of the forward data packet being successful is PRR. If it's IID transmissions and I have 80% probability that my packets are getting through, each time the probability it's getting through is 80%. Okay, because it's an IID, there's no difference from time to time. Similarly, on the return path, the acknowledgement has some packet reception rate as well. That's also the probability that I get the ACK back. The product of these two probabilities is the probability that I send a packet and I get the ACK back. Okay? Now we have a geometric random variable where it's like I'm tossing a coin and I'm waiting to ask how long do I need to keep tossing till I see a heads. In this case, till I see a success. And the probability of success in this case is just the product of those two. Right? So the PRR of the forward direction times the PRR of the ACK. And so the expected value of a geometric random variable for which the probability of success of is this would be 1 over PRR forward times PRR ACK. Now, this number is often close to 1, can be ignored. Why is that? Because ACK packets in many systems are very, very small compared to the actual data packet. So if I'm sending a data packet of, let's say, 1500 bytes, and the ACK packet is maybe 10 bytes, now the data packet is about 150 times longer than the ACK packet. That means it has 150 times as many bits than the ACK packet. If my probability in the forward direction is reasonable, let's say between 0 and 100%, it's a pretty high likelihood that there's this many bits being sent without a problem, right? And if you think about how the packet reception rate might vary as a function of the number of bits, it's going to decrease exponentially fast. Because even if I want to say that, if I have like 4 bits in error, I would lose my packet. Well, getting 4 bits in error out of 1,500 bytes is exponentially more than getting 4 bits in error out of just 10 bytes. So if this is some reasonable number, this is often like arbitrarily close to 1. Okay. So for small ACK packets. So if the ACK packets are very small, almost always they'll be received. If larger packets are received with some reasonable probability. And so if you ignore that, it's sort of 1 over PRR. Sometimes we just take this approximation and we use that as our ETX metric. So certainly it favors high PRR links because if I minimize my ETX, I'm choosing a high PRR.
The node is trying to figure out the ETX. It will keep on transmitting until it gets an acknowledgement. If we do not ignore the reverse acknowledgement, then how will it figure out like?
Yeah, so I'm going to come to that in just a second. So let me table that question. I'll come to it. This statement is a purely sort of a mathematical view. I want to talk in a bit about how do we actually empirically calculate and estimate ETX. So there we don't even talk about doing a calculation based on PRR. We literally measure how many times I have to transmit, and that measurement takes into account the X. The key point here is that this number is so close to 1 that you can kind of ignore it for the purpose of the calculation. But when you're actually estimating it, yes, you do need both the forward packet and the ACK pack. The point is that these ACKs failing is a very rare event. So one reason why the ETX tends to do well is that you tend to pick good quality links. The second is that it's sort of ETX is correlated with lower energy usage. So in the case that it's a wireless sensor network, those nodes might actually be running on batteries. If they're embedded, in the roadway, they may or may not have power that's constantly supplied to them. You need them to still last a few months, if not years. Then a network in which you're using ETX as your metric, you tend to pick links where the nodes won't have to repeat that transmission over and over again. Each time they have to send a packet, they're going to consume battery. And so by reducing the ETX, we're also reducing their use of the battery on the transmitter side. So that's one way in which you might be improving the performance is from an energy perspective. ETX is correlated with lower in-network interference. So if you preferentially select links that are less likely to need repeated transmissions, you're reducing the number of total transmissions in your network, which means you're reducing the number of interference between links within your network. Okay? So not only does it solve the almost like the physical layer problem of picking good quality links, it's also solving the link layer problem of reducing interlink interference. Okay? So reduces interlink interference, and as you can imagine, with what this will do is it'll basically increase the network throughput. Okay, so it's good for, right, item number 1 is it favors high PRR links, meaning resulting in higher reliability. So you have less chance of losing your packets. Second, it's correlated with lower energy. Third, it's correlated with higher throughput because you reduce the overall interference load on the network. Fourth, ETX is correlated with lower link latency. So now, because on average it takes me fewer transmissions to move my packets through, it also means that it's taking me less time to move my packets through. I don't have to retransmit each time. That would be an additional retransmission delay. So from a retransmission delay perspective, ETX is also the best thing to do. Not just for reliability, not just for energy, not just for throughput, but also delay. Right? So this improves network delay. Right? So it's like this one metric not only handles reliability, it also handles or is positively correlated with other things we would care to improve in our network, such as energy, improving throughput, reducing latency, and so on. So this metric is very robust and sort of multidimensional, and for that reason, we end up using it a lot in these multi-hop wireless protocols. So this use of a metric-based routing protocol in wireless networks is in some sense an alternative to the blacklisting approach that we talked about here. In the blacklisting approach, you don't need ETX in anything. You've sort of prefixed routes to only use highly reliable links. All of your links have an ETX close to 1. There's no reason to use ETX as a metric. They're already sort of built into the system, right? But if you don't do blacklisting or cannot do blacklisting and you have a network where you want to improve reliability, latency, throughput, energy efficiency, ETX offers you sort of this one-size-fits-all type of a metric. And so that's one reason it's become very popular and it's used in many deployments. For example, the NetBlazer system that they've deployed essentially uses some version of ETX. I mentioned RPL as a IETF standard that uses ETX as a metric. So there are many, many deployments that end up using some version of this in their system. So that brings us to sort of practical estimation of ETX. And in most network protocols which want to use ETX as a metric, you have to compute for each node, for each of its neighbors what the ETX value is. And typically it's done based on empirical counting of retransmissions. So you just simply count. Every time you have to send a packet, you count how long did it take you to send the packet, how many times you had to retransmit it. But also you want to averaged over the past with a what's called exponential moving average, with an exponentially decaying weight. So what does this look like? Sometimes it is referred to as EWMA. It's called exponentially weighted moving average. So it says something like ETX estimated at time or at particular packet, let's call it n+1, is the estimate that you had at the previous packet multiplied by some factor alpha plus 1 minus alpha times the ETX estimate for the current or instantaneous packet. So what I mean is that you send a packet, maybe it took you 2 tries, that's this number. This is your previous estimate of the ETX, and we're weighing that previous estimate by some factor alpha and the current value by some factor 1 minus alpha in such a way that alpha is just some number in 0 to 1, typically something like 80% or so. What this does is that your previous estimates are getting weighed by a factor of alpha. Over time, an estimate that's like 2 time steps ago, the measurement gets weighed by like 1 minus alpha the first times it shows up, and then an alpha the time after, another alpha the time after, another alpha the time after, and so on. So basically, as time goes on, any particular value that you measure, its impact on a future estimate decays exponentially with the number of packets that have passed between now and then. Okay, so that's the sense in which it's an exponentially weighted moving average. Empirically, people figure out what's a good value of this alpha to, for your estimator. If alpha is large, okay, we have more weight to past measurements. And on the one hand, that could be good because this could help you smooth out any instantaneous errors, right? Can help smooth instantaneous noisy measurements. Okay. So this, in fact, property of the exponentially weighted moving average is exactly the same as a low-pass filter, a digital filter, in which if this number was sufficiently high, it's like you're giving a more smooth estimate. You're sort of filtering out the high frequency components. And so if your instantaneous measurements are very noisy, having a large value of alpha sort of helps you stabilize the estimate. On the other hand, if too large it's not dynamic enough. It's not dynamic or responsive to changing conditions. So in particular, if I have a much faster scale at which my link qualities are changing, I might want to make my alpha a little bit smaller so that it can quickly tell me if the link has gone bad now. I don't want to stick with an older estimate saying the link is good because the past 100 measurements were good, but the last 4 measurements have all been disastrously bad. The link quality has changed, but because the alpha is so high, I haven't quite adjusted to the changing conditions. And so the value that ends up getting chosen empirically provides a trade-off between these two extremes. Okay. So my point being that even though you can say mathematically if the packet losses were IID, I could just measure the fraction of packets that went through, I can just take 1 over that and that would be the ETX. In practice, the channels are not IID. We've talked about this. If you have fading environments, there is a lot of correlation between time samples. If a packet was just sent successfully, probably the next packet is also going to be successful because maybe that fading signal is above my threshold still, right, because of temporal correlation. And so in practice, we wouldn't want to take an assumption like this into our protocol. We would want to empirically calculate it, but we still need to have a balance between, one extreme would be my ETX estimate is just my current value, and that would just be too noisy, because just on one particular sample going bad makes me think the whole link is bad, and that may not be true. Or at the other extreme, I don't want to be so tied into the past that I'm not able to change it. So this is the trade-off we end up striking in practice. And so if you look at a practical implementation of a multi-hop wireless network, you already have an idea of how to go about doing it. You would want to measure the packets as they go on across links. You would use an estimator like this to estimate the ETX on all of the links. You would then use a layer 3 network protocol that's doing like Bellman-Ford or Dijkstra on the measured value of the link qualities coming from the ETX calculations. And so you compute the shortest path, not shortest path in terms of hops, but the shortest path in terms of the ETX count, right? Yeah.
All these are applicable for static and mobile.
So, yes, they can be applied to both static and mobile networks. Mobile networks need a little bit more care because even your neighbors might be changing over time. We'll come to them. So far, much of what I'm talking about is directly applicable to static networks. For mobile networks, there's a little bit more you have to think about. So if you combine with a layer 3 distance vector or link state protocol to compute, or as it can, to compute shortest end-to-end paths, shortest cost that minimize the sum of the ETX. Let's say E for E in the path, right? So all the edges that are in the path, if you add up the ETX values, that's the total metric that you're minimizing if you run Dijkstra or link state over this metric. So a good question was asked, is this for static or mobile networks? Let's say for now it's for static networks. Even for mobile networks, you can use this for the period of time that the nodes are not moved out of range. You can, but it's not the best choice. And we'll see that the way, for example, the trellisware system operates has nothing to do with ETX calculations at all. It turns out to be a far more robust approach than doing either reactive or proactive routing using a metric, but you can. What else do I want to say? Oh, just as a quick sort of passing statement, for example, the RPL protocol that I mentioned is a distance vector-based mechanism. The thread protocol that I mentioned also in this context, that's a link state protocol. And at the core of it, typically they'll use something like ETX. But today, if you want to go back home, you have a bunch of multi-hop nodes, you want to program a routing protocol, you can take ETX, you can take shortest path routing, either distance vector or link state, and you can get something that's up and running and functional, right? And with reasonably good performance. So we'll stop here for today and continue in the next class.